Now discuss the important topic, which is ionization energy, the next topic. So ionization energy is the energy required to remove an electron from the outermost shell of isolated gaseous atom. So what happened here is, if A is an gaseous atom, so if an electron is removed, then the positive charge will come here. So this is called ionization energy first of A. And when again, if this is one electron is removed from this positive charge, then it will become 2 plus, and this is called as ionization energy of A plus, or the A, or we can say that simply it is the second ionization energy of A, and this is called the third ionization energy of A if an electron is removed from this. So what is the del H change in enthalpy is collection of all this ionization energy, IE1 of A plus IE2 of A and IE3 of A. These are called successive ionization energy. So what is the order of successive ionization energy? If we ask, then the order of successive ionization energy will be IE1 of A is very small, and IE2 of A, and it is also very small as compared to IE3 of A. So these are the successive ionization energy. So we know that when the Z effective is increasing, effective nuclear charge is directly proportional to the ionization energy and inversely proportional to the size. So now let's discuss about the factors affecting ionization energy. So there are some important factors which will affect ionization energy, such as it is directly proportional to the Z effective or effective nuclear charge and inversely proportional to the size, and it is also directly proportional to the fully filled and half filled electronic configuration So this is only applied in period of periodic table. So let's take an example of comparison, and let's discuss the comparison between the second period, which is lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine and neon. So we compare the first ionization energy. So to compare this in period, we need to write their electronic configuration. So it has 1s2, 2s1, this has 2s2, this has outermost electronic configuration of 2p1, it has outermost electronic configuration of 2p2, 2p3, 2p4, 2p5 and 2p6. So according to the general order, if we go left to right, the size decreases. So if the size decreases, ionization energy should be increased, but it is not applicable in general. So the order of ionization energy can be affected by this is fully filled orbital. We know that fully filled subshell, and this nitrogen is also half filled because P can fill only 6 electron and 3 is the half value, and this neon, it is also fully filled. fully filled shell. So the order of ionization energy, फर्स्ट आयोनाइजेशन एनर्जी का ऑर्डर की अगर बात करें तो ये हो जाएगी बेरिलियम. So let's take from the first. The lithium will be the least. Then if it is fully filled, then it will replace the next atom. If it is half filled, then it will replace this atom. So boron will be here, and then beryllium will be here. So this is an order that we see. After that carbon, and then oxygen, because this is also changed due to the half filled and full filled condition. So oxygen, and then nitrogen, and then fluorine. Oxygen, nitrogen is also here, and then fluorine, and in the last neon, which has the highest ionization energy, which means when removing the outermost electron, the highest amount of energy is required from neon, and least amount of energy is required for lithium, because and that is why lithium will easily form positive charge and donate its electron, and it is a metal. Now for comparison of second ionization energy, for calculating the second ionization energy order, we need to remove one electron and see if it have the second ionization energy. And if we remove one electron from here, so it will become 1s2, and there is 0 electron in 2s. Here it is fully filled, but now it will become s1. Here it will become p0, here it will become p1, here p2, p3, p4, and here p5. So this will be the second ionization energy order, electronic configuration. So according to this, the order will be beryllium, and if it is half filled, then carbon will be changed to nitrogen. Beryllium, then carbon, then boron, then so here some exception has been seen. Lithium will become the most energy because 2s, because it has the most stable electron configuration. 1s has the highest attraction to nuclei, that is why it will become the most ionization energy to break this lithium ion. And here fluorine and oxygen will be interchange, oxygen then fluorine, because of the half filled, because oxygen have half filled, so it will overtake fluorine. And same can be speak about this carbon and boron. So this boron is fully filled, and it will overtake this carbon which came before it. So this is the final order of second ionization energy of beryllium. And there is one note to be remembered, that speak is helium has the most ionization energy in periodic table. So it is the most ionization energy in the periodic table, helium. Now let's discuss about some groups. Just like in group 1 periodic table, as you can see, the expected order is, if we go down the group, the size will be increasing, and ionization should be inversely proportional to size, so it will be decreasing. But what happened here is this francium and cesium, this will interchange due to presence of the size factor. Same can be applied for this size of it PA, due to presence of a block, it will increase. And if we talk about the group 3 to group 12, there is a trick to remember all the ionization energy for this molecule. As you can see, from the group 3 to group 12, the electronic configuration of the D group, D or D shell, the ionization energy order of third group is seen to be the SC, and Y and La, the size factor and electronegativity inversion. So this can be applied here. But for the group 4, 5 and 6, group 4, 5 and 6, which is the Ti, B, Cr and Ni, जिसको in short we can speak as Tucali, ionization energy increase down the group. So this is an example. You need to remember that it is an exception here. Now let's see for the third group. For the third group that is present, only the except third group and Ti, V, Cr and Ni, we can use stick sign. So we use this graph according to which a 3D is come first and then 4D and then 5D, and this is only in group 7, 8, 9, 11 and 12. So for ionization energy we use this 5D come first and then 3D and then 4D. So this is an order for these groups, these columns. And there is a question asked in net, the correct order of ionization energy is. So the according to this right trick which is applied here, so this will be the right answer. So now let's go to the group 13. So for this molecule we use a W according to which the group 13, the ionization energy order can be boron, tellurium, gallium, aluminum and tin. Due to inert pair effect we can explain this Ti and Ga. So this will be the group 13. Now let's go to group 14. So for group 14, the carbon family, after we know that down the group the silicon, we know that down the group the size is increasing. So ionization energy has to be increased, but due to inner pair effect, same this Pb and Sn will change the position, and this type of graph can be seen here. So this is the order of ionization energy. Now let's discuss about the electron gain enthalpy. So it is the energy change when an extra electron is added into the outermost shell of isolated gaseous atom. When an electron is added to the system or the nuclear outermost shell, so this is called electron gain enthalpy, and it is represented by del H. So if an electron is added in the gaseous atom, it will become negatively charged, and this del H will be negative. And if let's take an example of oxygen, which has a 2p4 and plus 1 electron is added, so it will become oxygen with 1 negative charge, and the number of p orbital, the number of electron p orbital will be 5. So the del H will be negative here because energy is released, and when the negative charge of anion, one additional electron is present here or added here, so it will become 2s, or it is a stable configuration. But instead of stabilizing, this negative charge and this negative charge will repel itself, and we need to give more energy. So this is positive del H, we need to give energy, and here energy is released, and here we have to give energy. And what is electron affinity? Next topic, electron affinity or electron gain enthalpy. So these are the same basically. इलेक्ट्रॉन एफिनिटी इज द इलेक्ट्रॉन को पाने की चाहत जिसके पास ज़्यादा है वो इलेक्ट्रॉन एफिनिटी कहलाती है. जस्ट लाइक दिस इज 500, 300, 200. Let's say these are the example or the anything like that. So electron gain enthalpy is negative of this same number. It will be in the negative charge. Negative sign will tell us about the release of energy. So there is a general trend, as you can see, when electron affinity and electron gain enthalpy is directly proportional to the Z effective and inversely proportional to the size. So in group 17, as we know that down the group the size is increasing and electronegativity decreases. So this should be the assumed order of electron affinity, but this is not seen because of the fluorine small size. The extra electron can cause inner electron repulsion and make the electron affinity and decreases the electron affinity. So the correct order is chlorine, then fluorine, and bromine and iodine. So this is the order of electron affinity. Why is this happening? Because chlorine has the highest electronic affinity in the periodic table. Chlorine. So this is an important note to be noted that. So these are some orders which is we know that down the group electron affinity order is cesium, then sulfur, then cesium, then tellurium, then oxygen. Because of the oxygen small size it will be least. And in group 15, as we know the nitrogen family, nitrogen, phosphorus, arsenic, antimony and bismuth. So we know that down the group size is the down the group electron affinity order should be this. And this has to be expected, but this is not happening here. It is only applicable in there. So AS, SB, AS, then SB, then bismuth, and these two groups will be go down. So this will be the electron affinity order. Now let's talk about the modified electronegativity. So what is modified electronegativity? It is used for hybridization. It is used with hybridization in molecules. So here what happened is, so to compare electronegativity of atomic size, we know that carbon with sp3 is the electronegativity is lowest, and carbon with sp2 and carbon with sp3, according to which, but instead of carbon sp3, n sp3 will become in between these two. And so this is the concept of group electronegativity, in which a carbon with CH3 group and one nitrogen with CH2 group has been this electronegativity, but after getting F2 instead of H2, this has more electron group at a high electronegativity group attached in fluorine, so it will attract more electron towards itself, and the tendency of carbon to attract electron from A will be increases. So it has more electronegativity as compared to NH2. Now let's discuss about the scale of electronegativity. So there are three scales or concept given by the scientists. First is Pauling scale, second is Mulliken scale, and third is Alvarado-Rocho electronegativity scale. So these are some important formulas of this. In Pauling scale, it will tell about the relative study, which will compare one with another. And in Mulliken symbol, we discuss about the absolute study. We do not do a relative study here. We do absolute study, and will give exact answer for this. So Mulliken scale in Mulliken scale we talk about the electron affinity and ionization potential. And in Pauling scale we discuss about the bond energies, and in Alvarado-Rocho electronegativity scale we discuss about the Z effective and R square. So these are some formulas and represented by psi AR for Alvarado Rocho, and psi M for Mulliken scale, and psi del psi for Pauling scale. So these are all the important formulas given here for calculation.